Hello, everyone, and welcome to another episode of In Plain English. I am your host, Jamie Moffa, and this is the last in the series of episodes called Interviews in Pain Research, where I spoke with researchers at the United States Association for the Study of Pain conference earlier this year. You can find the posters for this episode and for all of the previous episodes on the website at inplainenglishpod.org. We'll be back at the beginning of the month with a very special interview that I conducted while at another pain conference last month. So without further ado, let's get to the episode. Our first interview this episode features Kathryn Braden, a postdoctoral researcher in the Castro Lab at Washington University in St. Louis. For her research, she used CRISPR-Cas9 gene editing to delete a endogenous opioid, meaning a opioid that your own brain produces, in a region of the brainstem called the DRN. And then she investigated how deleting this endogenous opioid affected mice's responses to pain.
So can you start by introducing yourself?
So my name is Kathryn Braden. I'm a postdoc in the Daniel Castro Lab at Washington University in St. Louis. And I study endogenous opioids and their effects on motivation and affect. And I'm starting to look at them in the role of pain.
Yeah. Can you take me through your poster?
Right. So we're interested in enkephalin specifically. So that's an endogenous opioid that activates mu and delta opioid receptors. And we're interested in its role within this DRN subregion. So the dorsal raphe nucleus is a brain region directly underneath the periaqueductal gray. And so everybody is really well familiar with the periaqueductal gray because it's known to affect descending pain modulation. But the border between the DRN and the PAG is not very well defined, and especially early studies that looked at a lot of effects of the ventrolateral PAG also could have hit parts of the DRN. Like, how do you differentiate between those very near subregions?
Yeah, and just for the podcast audience, this is more of a general audience. Yeah. This is all in the brainstem.
Brainstem, yeah. So this is like the midbrain, so kind of close to like your lizard brain type of stuff.
Yeah.
And so it's not doing any like super high order functioning, but it's still very important, and we're interested in what the enkephalin is doing there.
Yeah, absolutely.
So we use a CRISPR-Cas9 viral approach. So we're using the CRISPR viral protein to knock down the enkephalin within the DRN specifically. And then we're just running a battery behavioral test to see whether knocking down this one precursor to this peptide is affecting any aversive or appetitive behaviors at baseline.
Okay.
And so what we found so far is that at baseline, when we test for mechanical sensitivity with our von Frey filaments, which measure the force that an animal is able to withstand after.
You are literally just poking the mouse in their paw and seeing what happens.
Seeing if they withdraw or not.
Yeah.
And usually higher thresholds they withdraw, lower thresholds they don't at a baseline state. And that's what we see with both our animals that have enkephalin in the DRN and animals that don't. Daniel, my PI, has always said that opioids are very modulatory, so they're usually state dependent. And so he was interested to see whether if we modulated the state of the animals, if that affected their mechanical sensitivity at all. So we chose to do a low dose of carrageenan, which is it's an inflammatory modulator. I think it comes from seaweed, and it's used in food preservation and stuff, but it just causes this short-term inflammatory reaction. And we gave it intraplantar in the paw at a very low dose. And in our wild-type animals, we get this moderate reduction in their paw withdrawal thresholds. But in our pre-positive animals, or the ones that have enkephalin knockdown in the DRN, they had this hypersensitive reaction. So they respond at even lower thresholds than the wild types, just from knocking down the enkephalin peptide in the DRN.
Yeah, this is endogenous opioid precursor.
Yeah,
yes.
Which makes sense because that's what you would expect in the PAG as well. So that kind of gives credence to the idea that the PAG and the DRN may be doing similar things, but maybe not exactly the same.
Right.
Yeah. And so we're also interested in other affective behaviors. And mice are very odor driven. And so we also started to do an odor preference assay where they're exposed to these filter papers with this chemical odorant on them, either IBT, which is aversive. It smells kind of citrusy, and I guess they really hate that.
I was going to say, that sounds nice to me.
Yeah, well, the putrescine, which is their appetitive odor, smells like trash.
I was going to say, like, if humans named it, I was like, oh, that one must be the aversive one.
No, not for mice. It's the opposite.
No, I guess it's the same for dogs, right? They're like, ooh, poop, let me go smell that.
Yeah, crazy animals, but that's what they like. And so we see in our wild type animals, they spend about 7 to 8 seconds less interacting with the IBT filter paper compared to a filter paper with water on it. Whereas with the putrescine filter paper, they spend around 5 seconds more interacting than water. So they're attracted to the putrescine, they're averse to the IBT.
Yeah.
However, our Cre-positive animals are way more, avoid the IBT odor way more than the Cre-negative animals, which was really striking to us and really exciting. And the putrescine effect seems to be hit or miss. But we've got to power that up and see what happens when we do further analysis. And further, with a lot of our other appetitive behaviors like food intake and social interaction, we didn't see any differences with the wild type or the enkephalin knockdown. As well as time spent in the open arms of an elevated 0+ maze or elevated 0 maze, which is a measure of anxiety.
Okay.
So there doesn't seem to be any differences in these behaviors at baseline, but there seems to be an aversion to odor and an aversion to mechanical stimuli under an inflammatory state.
Right.
And so me being from a pain background, I was interested to see whether whether there were any effects in a pain model, whether enkephalin activation could be used therapeutically in this particular brain region. So I did a pilot study looking at DQ dread expression. So these are designer receptors exclusively activated by designer drugs. And so we're expressing this receptor in the enkephalin neurons just within the DRN and giving a drug that's only going to activate those receptors. So we should be selectively activating just those neurons. And when we do that on mice that have gotten a spared nerve injury surgery, we see an increase in their paw withdrawal thresholds or an alleviation of their mechanical sensitivity after about 1 hour after that dread agonist.
So these mice kind of have neuropathic-ish pain.
Yeah.
Yeah. And so then when you're activating these neurons in this area of the brainstem, it's not quite bringing them back up to baseline, right? But it's making them a little bit less painful.
Yeah. And this is just a pilot study, so we've still got a lot more exploration to do on that, but it does seem to improve their mechanical sensitivity. And I would like to look at this with more of the affective and motivational behaviors that are affected by chronic pain as well.
Right.
Because that's also a huge issue in preclinical pain research, is only looking at these reflexive behaviors. So that's also a future direction to look at. Yeah, I know, right?
I just don't have time.
It's my whole PhD.
Yeah.
That's what I'm trying to do in my postdoc, and I still haven't gotten to it.
Yeah.
And so that's promising for the future, and we're going to follow up on that. We're also interested in particular subpopulations within the DRN. So we're looking at glutamate and GABAergic neurons and trying to knock down enkephalin just in those specific subtypes. And what we found so far is that when we knock down enkephalin in VGLUT2 neurons specifically, so these are glutamatergic neurons that express this one particular transporter, they are more hypersensitive to this carrageenan injection, similar to the whole DRN knockdown of the enkephalin.
So it could be just those, and the glutamatergic, for the audience, those are the excitatory ones.
Yes.
So it could just be those excitatory neurons specifically.
Mm-hmm, yeah. Yeah, which would be interesting because so the BGLUT2 and the BGLUT3 population, you would expect them to be doing the same thing. They're both glutamatergic, so they're both excitatory. But what we've seen so far, we want to do more comprehensive in situ analysis of where these neurons are expressed and how they're overlapping.
Right.
But so far, we've seen that BGLUT3 is mostly expressed just within the medial portion, so the middle portion of the DRN, and BGLUT2 is kind of expressed more in the lateral wings, which is kind of interesting because when I do my CRISPR injections, I'm usually seeing the expression of the virus in more of the lateral wings. So that kind of makes sense that wherever that enkephalin is being expressed would also correlate with where the BGLUT2 is being expressed. So,
yeah, that makes sense.
Yeah, so we want to do some more analysis of the expression patterns and how they're overlapping. And then, as I was mentioning before, that can also feed into future circuit explorations of where those particular neurons are going if we can narrow it down to a very specific subtype.
Yeah. Thank you so much for recording this for the podcast.
Of course, yeah, my pleasure.
Our second interview this episode features Yolanda Campos Jurado, a postdoctoral researcher in the Morón Concepcion lab at Washington University in St. Louis. Her research focuses on understanding the connection between alcohol use disorder and pain, and specifically studying whether having chronic pain increases the risk for higher alcohol consumption. And she is studying this using a rodent model.
Can you start by introducing yourself?
Yes, so I am Yolanda Campos Jurado. I am a postdoctoral fellow in Washington University in St. Louis in Dr. Jose Morón Concepcion laboratory in the anesthesiology department.
Great. And so can you take me through your poster?
Yes. So I am interested in the relationship between alcohol and pain. So we know in general that people that drink alcohol are more likely to develop pain, chronic pain. But in my case, I am more interested in the other way around. So what happens in people that are drinking alcohol, and if they suddenly have pain, what's going to happen? Are they going to drink more? And it seems that that's what happens in humans, that people that have higher levels of pain also drink more in general. But because we also need to see what happens in the brain, and we need to be able to do that in animal setup. So in my case, I'm trying to do that in rats in the lab. So what we do is we train these rats to go to a little box and press a lever, and then they get some alcohol.
Tasty.
And they kind of like it, so that's good.
That's good.
And then what we do is after they're trained, we make them have pain. So to some of them, we inject something in the paw that's going to cause an inflammation, and they're going to be in pain for around a month. And what we're interested is in knowing what happens in the rats that have pain compared to the rats that don't have pain. So for that, after they receive this injection, they keep going into the boxes, and they have different doses of alcohol. They have 20, 30, or 50% alcohol.
That's all really strong.
Those are very strong doses. But it's true that in the people when people have alcohol use disorder, they usually drink very, very strong alcohols too.
Right.
So that's what I was trying to see if they could behave like humans, kind of. And because I have a lot of graphs, I'm just going to go to like the main part of it.
Yes, yeah.
So basically what I've seen is that when we look at how much these animals are taking in the boxes, when the animals are in pain, they seem to prefer less let's call them medium doses, the 20% dose, and they increase and catch up with the control animals for the really, really high doses. So, and that happens in male animals and in female animals, although it seems that it's a little bit stronger in males, and we still don't know why this is happening, but it's very interesting. And I was also interested in knowing what happens in males versus females, because it's important that we also study sex differences, because it could happen that there's differences in the brain mechanisms involved in these behaviors.
Right.
But basically what I see is that when animals are in pain, their dose response is shifted to the right, which means that, as I was saying, animals will drink more from higher doses, and animals will drink the same as their control animals, only for higher doses. So that could, if we translate that to humans, could be a risk for, if a person develops pain, then that person could be only going to drink from the higher doses, and that could be like a higher drink, a higher risk for developing alcohol use disorder, for example.
Yeah, so that's like really interesting finding that, like, yeah, maybe people who develop chronic pain, then they'll shift their alcohol use to like stronger alcohol or just intaking more, and then that puts them even more at risk.
Exactly, yes, and we haven't seen like an actual increase when we compare to the control group, but that could be because of many reasons, because this session is only 30 minutes. This is like a very particular way the animals have access to alcohol, so unfortunately we can't measure many things in just one experiment. So it'd be really cool if more people study this, because there are very few labs doing this right now. So if you're there, please do more alcohol and pain research.
Yeah, no, that's really interesting, and a very interesting intersection between addiction and pain, and kind of showing how they overlap. Are there any particular like areas of the brain that you're interested in looking at to see about how they mediate this effect? Or
yes, we think that one like system that could be very involved in both pain and alcohol could be the kappa opioid system, just because we know that it's dysregulated in both pain and particularly any drug use, but particularly alcohol. So my plan right now, I have the brains of these animals, so I want to do a technique that it lets us measure the RNA of the different opioid receptors. So I want to potentially look into the amygdala, nucleus accumbens, VTA, and then probably go for at least mu and kappa opioid receptors, just to see if these differences in behavior correlate with differences in the RNA levels of those.
Yeah, that's really interesting. Thank you for presenting your poster for me.
Yeah, thank you.
Thank you once again for tuning in to this episode of In Plain English. Once again, our interviewees for this episode were Kathryn Braden from the Castro Lab at Washington University and Yolanda Campos Jurado from the Morón Concepcion Lab at Washington University. You can find both of their posters and the posters from previous episodes on the website at inplainenglishpod.org. Our logo is by the wonderful team at BioGraphics. That's Jessica Higginbotham, Tanya Lintz, and Yolanda Campos. Our music is by Sam Brunwasser. You can find more of his work on SoundCloud at Visuals Now Beats. And finally, be sure to follow us on Twitter, Facebook, and Instagram at Plain English Sci so that you never miss an episode or exciting news and updates about In Plain English. Again, that's PlainEnglishSci. Thanks once again for listening, and come back next time for another episode of In Plain English.